This is about solving absolute value inequalities. We're going to solve each of the following by graphing. So what it means to solve by graphing, well, there are a lot of different ways that you can solve by graphing, but what we mean right now is taking each side of this inequality and setting it equal to y. So we're going to graph y equals x minus 2 and y equals 1. And then what we want to do after that is we want to figure out where the red one, this x minus 2, where it has greater y values than the blue one, which means where is the red graph higher than the blue graph. So if I look at that, it's going to be where x is greater than 3. Likewise, we did the same thing for each of these. Y equals absolute value of x minus 2, and y equals absolute value of x squared minus 2. And then we're comparing those to y equals 1. So if we look at part B, it's everywhere that x is less than 1 and everywhere that x is greater than 3. So if we analyze these in terms of like being able to solve for them, that's something that is not rocket science. We've done these in classes before. So if we add 2 to both sides, we get x is greater than 3. And if we looked at this from Algebra 2, what we did was we would break this into 2 different inequalities. Once we get the absolute value by itself, then we'd see x is greater than 3 or x is less than 1. And those are the things that we also see visually on the graph. So we would graph the solution sets like this. And to write it in interval notation, we would say 3 to infinity or negative infinity to 1, union 3 to infinity, depending on which problem we have. Now, if we were looking at this problem, I graphed y equals x squared minus 2. And so in order to graph the absolute value of x squared minus 2, everything that's underneath the axis needs to be mirrored above the axis. And then we can trace this going up. So that's kind of freaky looking. But this red graph represents y equals absolute value of x squared minus 2. So what we have going on here is we need to find where that is greater than the blue line. And we have actually 3 intervals where that is the case. So we have these 2 intervals down here where it doesn't work, but then 3 intervals where it does. So our objective is to figure out where those are. These are pretty simple. This is at -1 and 1. Those occur, we can kind of just figure it out by playing around with it. What number is going to make this equal to 1? Well, if I plug in square root of 3 or negative square root of 3, if that gets squared, we get 3 minus 2, which is 1. So the intervals where this works are negative infinity, negative root 3, union -1 to 1, union root 3 to infinity. So if I graphed this, this is kind of what it would look like. -1, 1, and positive root 3. So that would represent my solution set. Oops, looks like I'm not going to be able to move it, but you can still see it. So if I'm looking at how to solve this, I would still break this into 2 cases because the absolute value is by itself. Then I would solve. I get x squared greater than 3 and x squared less than 1. And then the objective is I get x is greater than root 3, and x is less than negative root 3 when I take the square root of both sides. And then here I get x is less than 1, and x is greater than negative 1. Now, if I want to know what math words I would use in here, I would have an or and an and then this whole thing is like a giant or. So I have this is an or, this is an and. But that's really hard to understand, so that's why we taught the number line method. So if I'm looking at negative root 3 and positive root 3, and I'm looking at negative 1 and 1 inside of these things, I would plug in these numbers and see whether it works out. So I could say x squared minus 3 is greater than 0, and x squared minus 1 is less than 0. And I could use the number line method for these, and I would figure out that this is greater, this is not, this is greater, this is not, this is greater. Or I'm sorry, I'm looking for less thans. So this is not less than, this is less than, this is not less than. So if I was graphing this, I would see all of these things be true, and it matches exactly with what's highlighted in yellow. Which of the above inequalities would we describe as the set of all values of x whose distance from 2 is greater than 1? That's the absolute value of this, because if we remember from Algebra 2, absolute value of x actually represents distance from a value, or distance from what I like to call a center. So in this case, if I'm looking at the graph of this, I had 1 and 3. Notice that it's the distance from 2. So if I put 2 in the middle, and I look at how far apart it is from each of these things, the distance from 2 is greater than 1. So notice that all of my answers are greater than 1 unit away from 2, both to the left and the right. Find the set of numbers for which the distance from negative 13 is less than 5 units. So if I want the distance from negative 13, I would write x plus 13, and I want it to be less than 5 units away. So then I could break this into two cases. And I get x is less than negative 8, x is greater than negative 18. It's an and problem. I can write this in interval notation and graph it. And the good news is it makes a whole lot of sense, because negative 13 is here, and the distance away is less than 5 in both cases. Set up an absolute value inequality and solve such that we're finding the values of x such that 1/2 x is less than 2 units from negative 6. So I'm going to graph this first. What we want for 1/2 x, so our goal for 1/2 x is we want negative 6 to be in the middle, and then we want negative 8 and negative 4 because we want our distance to be 2 units or less, or I'm sorry, less than 2 units away. So that's kind of what our graph should look like. And I have 1/2 x plus 6 on the inside of an absolute value, and that's less than 2, which makes total sense because it's kind of just like this problem. So it is less than 2 units away from negative 6. Like if I plugged in negative 6, that would, I'm sorry, if I looked at this situation and I kind of graphed this, 1/2 x would kind of look like this, but that's not what x is going to look like. So x is going to look entirely different, and I'm going to break this into two cases and kind of see what x looks like. So if I solve this, I get x is less than negative 8, x greater than negative 16. So if I look at my graph, negative 16, negative 8, which means that my middle number is negative 12, and these distances are actually 4. Well, this is a little confusing unless you realize that we were finding it such that 1/2 x is less than 2 units from 6. So if I graph 1/2 x, this holds. But I'm finding the values of x. So if I find the values of x, what do I have to do to all of these things up here, including my distances? They all get multiplied by 2. And then this is going to be what my final answer looks like. So my final answer is actually negative 16, negative 8, even though that doesn't necessarily look like it jives with being less than 2 units away from negative 6. If I have everything in here being less than 4 units away from negative 12, that represents the values of x such that 1/2 x is less than 2 units from negative 6. Find the absolute value inequality statement that corresponds to these inequalities. So if I look at the middle of this, the middle or the center is going to be 21.5. So I want 19 here, and it needs to be filled in. 24 is over here. 21.5 is in the middle. And these are distances of 2.5. So I can write absolute value of x minus 21.5, which is the same thing as 43 over 2, is greater than or equal to 5/2, which is the same thing as 2.5. I can also write absolute value of 2x minus 43 is greater than or equal to 5, or a variety of other things that represent this inequality. Solution to this is negative 16 less than x less than 8. So I'm going to graph that real quick. The center of this would be at negative 4. And notice that my distances are going to be 12. So ultimately, when I find absolute value of ax minus b is less than 2, my goal is for this graph of a times x, because this is very similar to this problem. This would be a times x in this problem. So I want my graph of a times x to have b as the center and my distance to be 2 in either direction. So that's ultimately my goal. So what I need is I need 4. I need to match 4 up with b. And so if I'm doing that, b is really negative 4 times a. This value is negative 16 times a. And this value is 8 times a. So if I'm looking at all these things, I need to kind of have these things all figured out. And what I know is that the distances when I'm dealing with a graph of x are 12. The distances when I'm dealing with a graph of a times x are 2. So how do I get 12 equals x and 2 equals a times x? Well, I can make 2 equal to a times 12 because I know that the distance in the x graph has 12. So a equals 2 over 12, or 1/6. So that means that a is really 1/6. And so then I have to change all of these a's to 1/6. And now I can just multiply them together and figure out what happens. So negative 16 times 1/6 is negative 8/3. Negative 4 times 1/6 is negative 2/3. And 8 times 1/6 is 4/3. So that means b is negative 2/3. And if I wanted to write this equation, I'd have the absolute value of 1/6 x plus 2/3. Notice that if b was negative, this sign was negative, it's going to turn into a positive 2/3, and that makes sense from all the other things that we've done and what we know about horizontal transformations. That has to be less than 2. So that was A, and that's B. Finally, x differs from 2 by less than 1/2. So x minus 2, this represents my center. This represents my distance. So less than 1/2. I can solve this. X minus 2 is less than 1/2. X minus 2 is greater than negative 1/2. I get x is less than 5/2, and x is greater than 3/2. I have this 3/2 and 5/2, and interval notation would be 3/2, comma 5/2.